All right, welcome to class today. I, I did successfully record last week's lecture, but it didn't. I haven't put the links up to it yet, but you can access it at the same place as the other ones. But I'll put up the links on the Canvas page. All right, so today, yeah, sorry, go ahead.
We were able to record the second part successfully because I watched the first part, but
yeah, it's uploading. It's uploading right now. The second part, I accidentally flashed the grades for my other class, all the test grades on the recording, so I had to edit that out.
Okay.
So anyway, but yeah, it's uploading now. So it should be up there soon.
Thank you.
Okay. Well, I didn't spice up the presentation very much today. I mean, in terms of its white background, I should make it more exciting. All right. So today we're going to talk about two different things. We're going to talk about correlation and regression, and they're very related. They just have a kind of a slightly different purpose to them, and one builds on top of the other. Actually, the last chapter in the book builds on regression even further. And in years past, I only taught this course one other time. I combined 17 and 18, and the book author I think does that in the exercises. So what I did was I just made the exercises do all the exercises for the rest of the semester, because it's only 3 chapters, or just do 2 weeks from now instead of 1 week. Okay. All right. So we'll talk about other schedule things in a bit here. So basically, this is all about this last part of the book. This last part of the course is all about finding statistical relationships between variables. That's what the part 4 is titled in the book. So looking at things like here we have relationships between drug markets and homicide locations. That's a slide. I mean a picture. So the first thing that we're going to talk about is just correlation analysis. Correlation analysis is coming up with a number to represent how well two variables, we call them variables because they vary. They're different in different places, or different observations have different values. So correlation analysis is a measurement of how much they vary together. Okay? In other words, when one goes up, does another go up? When one goes down, does another go down? Or does one go up and the other go down at the same time? So that's what we mean by co-vary. Do they vary together? And that's a relation. That's basically a way to measure their relationships. Okay. So correlation analysis is the quantitative set of statistical methods to measure both the direction and the strength associated between a pair of spatial variables. Now, we say spatial, but they don't actually have to be spatial. As in this course, where most of them will be, but they could just be observations that aren't necessarily spatial, individual observations. So in whatever our data set is, we're looking at 2 different variables and seeing how those variables change with one another. So a non-spatial example would be, for a long time, well, actually it's still the case, but medically, well, that's not, anyway, I'm not a medical researcher, but for a long time we knew that the people that had smoked a lot also had more lung cancer. So smoking and lung cancer co-varied with each other. We may not have known that the medical cause for that, and I still don't know if all that's understood, but those two variables co-vary with each other, and that's not necessarily a spatial example. That's just looking at a table that would include a bunch of people and their smoking history and their medical history. Right. Anyway, a graphical representation of a relationship can be seen in a scatter plot. A scatter plot is a common tool for this purpose. I think most of us have seen scatter plots. We'll see a few more today, but that's what a graphical representation looks like. If we have a positive correlation, that means that both variables get larger and smaller together. So one example there is central place theory. There are presence of more retail services as population increases. Negative, the larger value of one variable corresponds to a smaller value of a second variable. In other words, as one increases, the other decreases. So here's a distance decay example. Pollution decreases downwind from a point source. So as we travel further away, so as distance increases, then pollution decreases. And then many times you'll find that you're looking for a certain relationship to exist, but there won't be a relationship, so it'll be random, where little or no association between variables exists. And so here's some scatter plots that show some of those scenarios. So here's a strong positive correlation. You see a scatter plot like this, where one is increasing and the other is increasing. That is a strong positive correlation. Weak positive correlation means that there's more errors. It means that there's more differences. They're scattered around. Strong negative, weak negative, moderate negative. So we get to come up with a number to kind of quantify the difference between this and this. Or that and that even. No correlation means that the points are spread out everywhere. And just to be clear, I know probably most of you understand this, but the scatter plot, the way it's created, is that in this axis is one of the variables, and this axis is in the other variable. And so we're just plotting the locations. So if this was, if this was distance on this axis, and on this axis would be pollution. So as distance increases, pollution decreases from a point source. Distance from a point source. All right, the positive correlation, the number of retail outlets in a census block or in a census tract would increase as population increases. Typically, with correlation, we don't necessarily have to have one being the one we're trying to predict or explain. In other words, population density can be thought of as a driver, right, for retail outlet locations. More people, more retail outlets. Okay? In that case, population density is the driver. It's convention to use the driver as the x-axis, or sometimes it's called the explanatory variable. And then what you're trying to predict, what you think is the response, as the y-axis. All right, so that's correlation. Well, with correlation, there may not be such a relationship that even exists. Okay, correlation is actually just trying to measure the strength of the association. So we're looking at the amount of point spread in that scatter plot. If it spreads a lot, we're going to be getting a lower value, a value closer to 0. If it doesn't spread that much, we'll be getting a value closer to 1. And by the way, we have a trend line on these plots, but typically when we're just talking about correlation, we wouldn't even have a trend line. When we're just talking about how much they're related to each other. But the trend line is useful for kind of seeing that relationship. When we talk about regression, we definitely put a trend line on there. So this slope of the trend line, in other words, the nature of the relationship, it doesn't have anything to do with the strength of the relationship, okay? Except for if it's positive or negative. So if it's correlated in a positive manner, going like that, it's more about the spread of the dots than whether or not it's a one-to-one relationship, this is almost like a one-to-one relationship. And as this is increasing, that's increasing on a one-to-one. And that makes sense because you can scale the data however you want it to. In fact, a lot of things that we measure, like distance, are made-up scales, right? Distance is you might be using meters, you might be using feet. So the axis itself is just a construct, like the distance. So whatever that distance really is, we could change it, and that would change the slope of the line, but it wouldn't change how strong or weak the relationship is. Yeah. The camera. Sure. Does that work?
No. Now I see you on the PowerPoint projector. And I still see the class on the here. Thank you.
Is that better?
That's right. Thank you.
Yep. Okay. I'll try to stay here too. I always forget that that's the better place to go. Okay. So one of the things to keep in mind is that correlation does not imply causation. Sometimes people state that slightly differently. Correlation doesn't mean causation. But there's all sorts of erroneous assumptions that can be established with correlation analysis. And correlation doesn't necessarily mean that there's a functional relationship between the variables, and that's why people say, well, correlation doesn't imply causation. So here's some examples. These are things that are correlated that obviously don't cause each other. Ice cream sales, as they increase, the rate of drowning deaths actually increases as well. And so those are both things that are correlated with it being warm outside. People want to eat ice cream when it's warm, and people want to go swimming when it's warm. And so they're related, but not. They don't. Obviously, it'd be ridiculous to say that ice cream sales causes drowning deaths. So don't eat ice cream if you don't want to drown. All right. So here's a little bit less obvious but still erroneous examples. Atmospheric CO2 levels and obesity levels, well, that's actually still pretty erroneous as well. So since the 1950s, atmospheric CO2 levels have been going up, and so has obesity. And although you may be able to remotely tie some of the things that would cause an increase in general obesity to there being more CO2 in the atmosphere, they're not related per se. And then sleeping with your shoes on is strongly correlated with waking up with a headache, and this is most likely due to some other lurking variable like working so hard that you're or spending other time doing other things that you just forget to take your shoes off, and therefore your head hurts because you're either not getting enough sleep or something. Okay. All right. So with correlation analysis, there may be a relationship. Okay, and that's what I was trying to get at before. And And so it's a good thing to use to understand how strong the association is between two variables. And then once you see that, you can use that to perhaps provide background and investigate whether or not there is a relationship between two variables. So typically, we call this x-axis the predictor and the response the dependent. So this is the predictor independent. This is the response. So here we're using latitude, and this is one of the data sets that we have available to us. So we'll experiment with the data set a little bit further. But we're using latitude to predict the average date of last spring frost. So as you travel further north, you will experience spring later, basically. And we all know that that's true, and that's the relationship there. So when we do correlation analysis, we are always going to get a value between 1 and -1. And 1 actually means that we have strong positive correlation. In other words, they vary together in a positive manner. -1 means that they vary together in a negative manner. Okay, that's the minimum value. You can't get greater or less than that value. And the 0 represents the total lack of any relationship at all. Okay. Using real numbers, it's even with things that really aren't related, you're going to get values very close to 0 sometimes, but they aren't exactly 0. So that's one of the things that we're going to talk about is actually using inferential statistics to see if the relationship itself is significant. And then you have to take that a little bit further. The book doesn't really talk about this too much, but even if it is a significant relationship in terms of statistics, sometimes it's not practically significant. In other words, there's still so much error that it can't be used. There's not much predictive power to be gained. All right, so there are two different correlation coefficients that we're going to talk about today that are used and they're both on the same scale from 1 to -1. One is basically used with interval ratio data, and the second is used with rank order data. So what we mean by rank order, we mean 1, 2, 3, 4, 5, 6, 7, and 9, 10, just ranked rather than in a number. Like interval ratio here would be, this is an example of interval ratio data. This is latitude, which is a number, and this is average date of last spring frost, which is a number, starting at 0 January 1st and continuing onward. All right, so as we've discussed several times earlier in this course, when we use interval ratio data, it's more powerful because we can use those numbers to quantify more exactly the nature of the relationship, and also it's easier to use in an inferential manner. So if you have interval ratio data, there's really no reason to convert it to rank order unless it deviates significantly from being a normally distributed population. It's one reason why you'd want to collapse your data. And that's the same as with other tests that we've talked about in this class. So the number that we're trying to get to is this covariation number. If when one changes, you can very, very precisely define the other, then we call that a strong amount of covariation. Okay. So the way that they're calculated is actually to look at the deviations from the x mean and the y mean. So we're not gonna actually calculate these things by hand. but we'll give you enough of the math background to understand what's going on. So if you look at the x-mean and the y-mean, those could be represented by these lines here, x-mean and y-mean. And we're looking at the deviations from those, okay? If the deviations are both similar, they'll appear in this first quadrant and this third quadrant. If the deviations are different, they'll appear in all four quadrants. So we can well, if they're opposite of each other, then they're the second and fourth quadrant. All right. So if we have points in only or most of our points in only diagonal quadrants, then we're said to have high correlation, whether or not it's positive or negative correlation. If they're in all four quads, then they cancel out, and it's close to zero. The deviations will cancel out. I think I meant to put a picture on there. But anyway, the correlation coefficient, which is sometimes just labeled, well, in statistics we used to use R to represent the correlation coefficient. The correlation coefficient is the ratio between the covariance in X and Y to the product of the standard deviation of the two variables. And then just from 0 to 1. So here is the way to test it, to come up with is this a significant correlation coefficient? Okay. The way that you test it is you get the R value. You can get the R value in a lot of different ways. Let's download the the book data, because this is the data that we're dealing with here. Workbook data. No, sorry. I meant the book data. What's up here? Book data. So we have this frost data in there. The frost-free day data. Open. Chapter 16. Last spring frost. Put that in C temp. And open it. Okay, so here this is the last spring frost day, and this is latitude. So book author's already made a scatter plot. It's the same scatter plot that we had up earlier. It's this scatter plot here. Okay. So once you make that scatter plot, you can actually get the correlation coefficient right off of that data. At least you used to. Maybe you have to click on the points. Yeah. Add trend line. That's only the R squared value, which we'll talk about in a second. And you could actually get the R value from getting the R squared value, but you'd have to infer, because what's a negative number times a negative number? It's always a positive number. So you'd have to infer whether this value is positive or negative. But we can see from it that it's negative. All right. Okay. So we could get the R square value, which we'll talk about in a second. So that's the R square value. Let's see if we can just get the R value. Yep. So we can do correlation right there. And we want to get the the latitude and the average last day of spring frost. I'll just put it right here. Huh. I didn't prepare well enough. Oh, this is probably it. Let's see what this value is, because it is positively correlated. So equals SQRT 0.7252. Yeah. So it's that value. Okay. So that's the right value. So the correlation comes out with this value here. That's the correlation between column 1 and column 2. The correlation between column 1 and column 1 is 1, as you expect. The correlation between column 2 and column 2 is 1. And then on this type of analysis in Excel, they just leave off half of the chart because it'll always be the same. So we could do the correlation between all of these variables if we wanted to. So if we change this to everything, in fact, we might even there we go. Okay, labels in first row. There we go. I messed up. Anyway. I'm just going to forget about the labels in the first row. Oh, okay. It did do it. I just was too quick. Okay, cancel that. Okay, so looking at latitude and the average date to the last spring frost, that's the correlation value. So we can see that the correlation between longitude and the average date to the last spring frost. Let's interpret that value, 0.13. What does that mean? Is the correlation very high? No. And why do you think that is? Why do you think longitude isn't related to the average date of the last spring frost? Yeah, east and west doesn't have much to do with it. Maybe a little bit because as you travel east, you're getting closer to the coast. And you can see that the second highest degree of correlation is actually distance to coast. So there is a relationship. It's not as strong, but there is a relationship between the distance to coast and the average date of the last spring frost. And we know that areas closer to water will have a more moderate temperature. So once they warm up, they won't be as influenced by rogue winter storm as areas that are further away from the coast. Interestingly, elevation is actually less related. You might think, oh, elevation's pretty related, but I mean, it's still pretty strong. Okay, but let's look at this test statistic, because this test statistic will be able to tell us if there is correlation between just because we have a correlation value that seems high or seems low, this test statistic will tell us if it's a significant correlation. In other words, is there a real correlation that exists in the population, because we just have a sample. So that test statistic is just the R value divided by this S value, okay? The standard error of the correlation estimate. And the standard error of the correlation estimate is also a pretty easy, this is a really easy thing to get. This is just 1 minus the R squared value, so take R and square it. And then we divide that by the number of samples minus 2. So basically the only thing that can change in there, that can vary, is the sample size. So as the sample size increases, you're going to be more and more likely to get an answer that it is a significant relationship. And so you're more likely to reject So let's just look at that real quick. So we could create a new one that says equals this times this, and kind of fill that out. Let's just delete these ones that don't matter, like they did. So these are the R squared values because we need that in the formula, and then we could just come up with we could just type that into the formula. Equals SQRT 1 minus this divided by n. What's n going to be? It's 76 because there's a label row at the top. So 76 minus 1, or minus 2. Minus 2. We can just put 74 since it's going to be the same everywhere. So then we could just fill this down again. Let's make sure that it used 74 the whole time it did. So this is basically the standard error of the correlation estimate. And then this math is actually just rearranging this. Okay, so we don't actually want to do this again. Well, I mean, we could, but we've already done this, and that's the denominator. So we can now just take r and divide it by the denominator instead of doing this math. But this math is rearranging algebraically that function. So all we need to do is a simple division thing. Just say the original r value divided by our standard error should give us the t statistic that we want. So that's the t statistic, and this is this is basically in standard deviations. It is a t statistic, so we have to look it up on the t table charts. It appears as though we're going to. What's the degrees of freedom? Degrees of freedom is just going to be the number of samples minus 1, which is 75. So 76 samples. So if we look at the T chart, we need to choose a level of confidence with our T charts the way they are. So we're off the charts here, so. So what that means is that they're all RT is off the charts. Degrees of freedom. Here we go. We'll just go to infinity, and RT is 0.8. That's the highest one. That's still not going to be significant. Okay. So we're in this realm. Test statistics for Pearson Dark and written like that. So all of ours are in this, which is odd to me. That should be higher. If I did that function right, just making sure. Square root. There we go. It's all about order of operations. Never mind. Okay, we can delete these guys. Oops. All right. So now we got much more expected numbers. Sorry about that. So it was doing the division before the subtraction. So that's what those problems were. So now we get a value of 13.97. Okay. So we're at infinity on the degrees of freedom in table C on page 306, and our t-value is now off the charts the other direction. So the highest value is 2.9. We got a t-value of 13.97601. So it's off the charts, and so the value is so small. The p-value is basically 0.000 after 3 significant digits for this one. Okay. All right. So now if we look at this, we are going to definitely, since the p-value is small, we're definitely going to reject the null hypothesis and say that there is a correlation between in the real population. Let's look at one that might be more interesting. This one right here, 1.1407 is going to appear on the charts. 1.4. Let's just go 1.4 because that's the closest value. Go out onto the chart on infinity and look at the value. What's that value there? Let's see if you guys get the right value. I just want to make sure that that's exactly right. 4192. So we got a value of 4192, which is really 0.4192. And so we subtract 0.5 from that value, and we get a 0.0808. So at the 0.05 level, that's still not. It's interesting that we're still not able to reject that at the 0.05 level. But if we wanted to use the 0.10 level, then we would be able to reject that. So depending on what our threshold is for rejecting, which is all about how much error we're comfortable with. So we're gonna make an error 10% of the time if we reject that null hypothesis in this case. So that is that's the correlation coefficient, and typically we're more concerned with just looking at the correlation, okay, rather than its significance level. We'll talk about trying to build a model from it later and see if the model is worthwhile by doing significance. Probably a little bit out of order slide here. Weather stations with a more northerly latitude have an average fall later than less northerly latitudes. So that's what we're trying to look at. So here's the linear relationship, which we've now seen in a few different ways. There is a test to see if the values are normal. We talked about it a little bit, but we actually didn't demonstrate it. But the KS normality test, talked about that before. So here's a work table. Even the book author says that this sort of value is rarely calculated. But if you wanted to go through and do it once by hand, you could. But that's definitely not required in this course. But you can see what's being calculated is the x and the y, the difference from the x and the y, and then the product of the x and the y, and we're comparing those xy differences to the product of the two in order to get that value. There's the same value we got, so we did it right. 13.82. It was really close to that. I don't know if it's the exact same. That's the value we got. 13.97. I might have messed up on the the n. What n is he using? 76. What n did I use? I used 74 minus 2 should be 76. But in any case, it's pretty close. All right. Now, there's plenty of weak relationships out there. Here's an example of a weak weak negative relationship between the cost of living and the percent growth of foreign-born populations. In other words, what we're trying to say here is we're trying to find a relationship between cost of living. As the cost of living, increases, we could say in general we have less of a growth in foreign-born populations. So there's more growth in lower cost of living areas. The problem is that it kind of looks like an L almost. So there is growth in lower cost of living areas of foreign-born populations, and there isn't growth in areas where there's high cost of living. Okay, but the relationship isn't one that co-varies with each other. Okay. I don't know if the book already points this out or not, but this may be something that is better to do as like an ANOVA, where you collapse and you say, okay, we're going to have high, medium, and low cost of living index areas, and test if the variance in those three areas is different, and see if that's significant. And it definitely would be. The variance is lower. Okay? So although we're not establishing, that type of analysis doesn't have the predictive power of what we're going to talk about today. In other words, if we were trying to predict the percent growth of foreign-born, like we were going to try to say, hey, let's make our town really expensive to live in, and we won't have a lot of foreign population growth. That might be true, but the opposite wouldn't necessarily be true. Just because you're in a low cost of living area doesn't mean that there is either a high or a low growth area. So, one thing that we could do to further the analysis is actually collapse the data. I talked about doing it in ANOVA, but what we could do is collapse it into ranks. So sometimes we call this Spearman's rank correlation coefficient. So we would use this in cases where we have ranked data, but also in cases where we have a highly skewed non-normal populations, if it varies significant from being normal. So here we've got two different categories. Is it business friendly? And yeah, 10 different categories, and then the response variable, is it been business friendly? So here are all the categories here. Okay. And these are the correlation coefficients between different categories. So the highest ones are technology and innovation and access to capital. Those are highly correlated. Infrastructure and transportation to technology and innovation is pretty high. Quality of life to cost of living is fairly negatively correlated. Quality of life, I don't know how exactly they're measuring that. But the Spearman's correlation coefficient is actually even easier to calculate. Here's the work table. You take the difference in the rank. So you've got a rank here and a rank here. Just line them up and rank them, high to low, and then sort them and number them, and then get the difference. So this means that there's a difference of -9. In other words, from this rank to that rank, you have to subtract 9 to get there. Actually, it's going this one to this one. It doesn't really matter which one you do.
How do you rank ties when there's more than two that are tied?
So that's a good point. That's why there's 0.5s here. So if there's more than two that are tied, you can average all three of those ranks, or four, or five of those ranks. So this is technically the average between the two ranks.
Okay, so they would all three would have the middle value.
Yeah, exactly. So, well, if it was three. So you would average 11, 12, and 13, and they would all have 12. Does that make sense? Now, if there were four, 11, 12, 13, and 14, you would average 11, 12, 13, and 14, and so they would all still be 12 and a half.
And then the next, so it would go 12 and a half more times than the next values.
Exactly. That's how you do it. Yep. Now, if with numerical values, that's going to be less likely to happen. But if you give you a situation where like more than half of your values are tied, it's going to throw off the analysis a bit. But so maybe find a way to untie them or something. Yeah, so this is the difference, and then this is simply the distances right here. The distance is squared. So 9 times 9 is 81. I don't know why that's a superscript. That's from the book. It actually should be, the subscript. That should be a superscript, right? Because 9 times 9 is 81. Yeah. So this is a pretty simple formula. Okay. This is table 14.3 in the book. Or 16.3. It's right in the book. Okay, it must not be right in my portion of the book. In my book. Yeah, it's not right in my book. 16.3. It's on page 249. Yeah, so in my book, this is a screenshot from my book. In my book, it's a subscript.
So my book is like your book, so what should be changed on
It should be a square, not a sub.
for that last one?
It should be d squared, like this, not d sub 2. Does it say, they say there's the same version, right? 3rd edition?
Yeah, mine's third edition.
Yeah, I think maybe there was 2 printings or something. One where there was more mistakes. You should put like the mistake-free version on yours. All right. Well, maybe not mistake-free. So these are squared. So this is a pretty easy formula, and you can see that that as this number increases, the sum of all these differences, it should make sense, right? That the sum of these squared differences, as that number gets bigger and bigger and bigger, you're going to have a bigger and bigger numerator. Your denominator is always going to be the same because it's just based on the number of observations. So as you get more, in the same analysis, you don't get more or less observations. You just get the same amount of observations. So that's constant for a specific analysis. So the only thing that could change is the differences. So as the differences increases or decreases, you get a larger number on top. Okay, and so that would mean that you get a larger value. And you're gonna range from 0 to 1 here. So as your differences get larger and larger, this number on the bottom will be able to divide into that number less and less. And so you'll get a bigger and bigger number, which will give you actually a number closer and closer to 0. So as this number increases, your value is going to get closer and closer to 0. Is the take-home message. Why that works. This is still read the same way as the other correlation coefficient, but this one's with ranks. And so that number right there, it still indicates a pretty high level of correlation. And then the reason why we're squaring them is to make them all positive. But yeah, as that value gets bigger and bigger, it indicates more of a relationship between the variables. Okay, so that's correlation. Okay. And the reason that we really talk, one of the main reasons we talk about correlation is to set up this next subject. Yeah, go ahead. Our what's that?
Yeah, page 243.
243. Okay.
What's the difference between those two formulas that they give?
16.4. Which two formulas?
Yeah,
I got 3.
16.
16.4 and 16.6. Well, the one at the bottom is just expanding the denominator, and actually rephrasing the numerator in a different way. It's it said usually when they say a computational formula is used to derive. Usually when they say computational formula, it programs better into like computer programming, so it involves less loops, is what I imagine. But that the numerator in that formula I can see is the same computationally as the numerator on the other formula. It's just expanded out.
So you can use any of them?
You can use either formula; they're equivalent.
Okay.
The bottom formula, that Sx and Sy is the standard deviation. So this is just the formula for the standard deviation expressed in a different way, the numerator. So the standard deviation of x and the standard deviation of y.
Okay.
The square root of all the square differences from the mean values divided by the total. So the x, see the second, in 16.6, the sum of x squared divided by n, that's the mean, and then you've got that's technically the squared mean, but then you've also got all the squared observations. So you subtract all the squared observations from the mean of all the squared values, and you take the square root, you get the standard deviation. It's just expressed slightly different than the way we normally express standard deviation, but it's the same mathematically. Because mathematically, because we'd say the difference between all the observations and the mean, but we'd square those and then take the square root. So we're just squaring in a different place, but it's still the same. So that's the standard deviation of x, the standard deviation of y in the denominator. And that's what's expressed in the formula. Okay. And then the numerator is just rearranging algebra as well. All right, so simple linear regression is a way to further measure two variables. But the goal here is that we're not only trying to find out how much they're related, but we're actually trying to establish, it says a functional relationship. Another way to say that is a mathematical relationship between one variable and another. So we're trying to mathematically describe the change in x, how that responds and causes the change in y. Okay? So because we're trying to establish that functional or mathematical relationship between the two variables, what we need to do is not use regression unless there's a clear rationale or model between the two variables. Next week we'll talk about how you can actually have more than one predictor variable. But today we're just going to deal with one at a time. Simple linear regression is used in so many different research areas. And if we look at regression as a whole, it's very common research tool. basically, it's a tool that we use to establish a mathematical relationship between multiple variables or a single variable. It's a little different than all the, I gave that example of ANOVA before. So with correlation, we could say, oh, well, we want to, we can see that they're not really correlated mathematically, but we can still see that there's a pattern, and we can still test for that pattern in another way. But with regression, we're coming up with a mathematical function that's going to explain the difference, and we need to be able to describe how powerful that mathematical connection is. That's one of the things that we're going to talk about. All right, so so here's an example. The relationship between precipitation and population density, or the number of county physicians and the county income profile, water acidity, and the distance from a pollution point source. Those are examples of relationships that we could look at. So we're always going to have a response or dependent variable, and then today we're going to talk about having a single explanatory or predicted independent variable. Those are all three terms that get used. The point is, it's the variable that's driving the other variable, the response variable. The application here is to identify a linear relationship between variables. Okay. So oftentimes there's two different reasons that you do this. One is you're actually interested in the mathematical relationship, because then you're going to take this relationship and use it to predict other areas. Okay? Like let's say you go out and sample a bunch of things and you come up with a relationship. You can use that mathematical relationship. If you only have the explanatory or predicted variable, you can use that to predict the response variable. So, in our simple example before, I could use latitude to predict the last day of spring frost, even in areas where I don't have the knowledge of the last day of spring frost. So it would give you a ballpark estimate. All right. Then the other reason is that once you create a mathematical relationship, you can actually look at the errors, the differences between the model that you created and the values that you use to feed the model. Okay, which we'll talk about these in a second here. I'll go back to here for a second. Okay, but imagine that there's a line in the middle of it. There will be in a second. And that's the mathematical model describing how if we go more northerly, we get our earlier spring frost day, or later spring frost day. We get a later spring frost day. So that line represents the model. The distances between the true value at that point and the model, those are the residuals, and they tell us a lot. If there's any pattern to our residual, there's probably some other variable out there that we need to think about. So it's, the other reason to run regression analysis is to examine and look at other patterns that might exist in our data. All right, so I didn't need to go back there. I was already on the next slide. So here's the, sometimes we refer to simple linear regression as ordinary. I left the word ordinary off, but ArcGIS calls it ordinary. Least squares regression. So what the line is actually, the line that's getting created is actually trying to do is to minimize these distances away from that line. That's what we mean by least squares. To make those square differences as small as possible. That's what that's the mathematical model that gets created. So here, if we go back to Excel for a second. Go back up to the chart. So that's the line that was created. So these are the differences. So in other words, our model, the model that was created, predicts that at 29 or 20, 29.2 degrees latitude, it predicts this value right here, but the actual value that was measured is right there. But the reason that it doesn't predict that exact value is because it's trying to minimize all these, so some of those errors are going to be off. But what this does imply is that the average of all these errors is 0. The average of all those residual values is 0. So here is the, it creates, there's 3 different values that regression analysis creates that we should be paying attention to. One is the R-squared value, which we already put on the chart here. We can also add the equation on there, and we can see the other 2 values which are significant, and those are the slope and the intercept of this line. Okay? Slope and the intercept. See, those are the same. No, they're not exactly the same, are they? 7.10. We must be using slightly different data, but they're very, very similar. 152 versus 151, and 7.117 versus 7.1097. So they're very, very similar. This one is the slope. It's in the other position in the book. So this is the book data that he gave, and this is just the slide from the book. So the slope is actually the number that's being multiplied by the x value, the response. So one way to read this is, if we look only at the slope, one way to read this is that a 7-degree change in latitude, a 1 degree change in latitude, causes about a 7-day change in the date of the last frost. So for every time you change x by 1, you're changing the frost by 7 degrees. That's one of the more useful ways of reading that. So that slope tells us kind of the average rate of change of all of your values. Now, obviously, there are exceptions, right? Like in reality, there are exceptions. Going from there to there, or even from here to there, we're going down. Even though we went more north, the frost came a lot earlier there. We don't know all the reasons for that. Probably has to do with elevation, I would think. But as a general rule, the trend's going this way. So as a general rule, a 1 degree change in the latitude causes 7 days difference in the frost value. All right, what about this one, this y-intercept value, negative 152.1? Well, that's not quite as useful. Okay? One of the reasons why he's making a big deal about it here, the book author is because as we go down in x, we're eventually going to get to 0 degrees latitude. And the intercept there is negative 152. That doesn't even exist because these are days since January. So if we get to 0 here, in other words, if x is 0, we should be trying to predict a value of negative 152, which doesn't make any sense. And so you, what you have to get away from this message here is that your predictive power goes totally away once you go outside of the domain of your x values. So our x values go from about 29 to 38. We don't really know much about what goes on in between here, or outside of these values. Those are outside of the domain of x. And in reality, we know that this is true because this value makes no sense at all. Also, if we got all the way up to 90, we might not know. What would the value be? And just do that on the calculator. So we'll use this formula. So if we got all the way up to 90, the North Pole, we're predicting the date of spring in the North Pole, the average day that spring will come, that there won't be any more spring, there won't be any more frost. So 90 times 7.1171. Okay, and then we need to subtract 152. Whoops. Sorry, minus another 30, because I messed up. Minus another 30. Okay. So that'll happen on the 488th day of the year. Okay, does that make any sense? There's no 488th day. And that's an extreme example. And it may be that if you were just barely outside of this, there's some predicted power, but there's no way to know. There's no way to know that. That's called extrapolation. When you take your regression values outside of the domain of X. Okay? All right. So, the sign of the slope indicates the direction of the relationship. The magnitude of B is the steepness of that slope. Okay. So it can be used, as I said, as the prediction, the predicted value. And you can use that to say, for every 1 degree of latitude, we're changing the day of the spring frost by about 7 days. Now, as we've already shown, all points, they don't lie exactly on the line. And this is because in nature, there's a lot of complex processes, even more complex sometimes when we're dealing with humans and how they interact. And we're trying to explain the variance, but there's still going to be variance. Even if we put multiple values in, which we'll talk about next week, we still can't explain all the variation. Sometimes there are random occurrences. Sometimes there are inaccurate measurements. If we want to come up with a measure of the strength of this relationship, we're going to come up with a way, and it's going to be related to what we talked about before, correlation. This correlation coefficient tells us about the strength of the relationship. So before we get there, let's talk about this analogy that the book author discusses, and that's this sponge analysis. So our model that we create that shows it's basically y equals mx plus b, and we're getting m and the multiplier of x. Then, the intercept. Our model is going to explain some of the variation. So we're going to think about that as a bucket. The bucket is filled with a bunch of water, and that represents all the variation that exists, all of the points. Okay? The stuff that's absorbed by the sponge, we're going to refer to as the explained variation. So after we run the model, we're going to see that this trend line explains some of the variation, but all of the residual values, the variation in the residual values left, that's the unexplained variation. The unexplained variation. We even took that analogy from somebody else, but the way that we can think about a number that's going to tell us about the predictive power of our relationship is a ratio of the explained variation divided by the total variation, or the unexplained variation, total variation, and 1 minus that value. Okay? Because the explained variation and the unexplained variation total up to be the total variation. So it's either explained or unexplained. It either soaked up by the sponge or stayed in the bucket, but that's the total. So the ratio of the unexplained variation to the total variation, the explained variation to the total variation is actually just the R value squared. So when you calculate R, if you take the R value squared, it works out to be the explained variation divided by the total variation. So it can be now it's going to be on a scale from 0 to 1 though. Okay? So here's an example of an R squared value of 0.9. See? An R squared value of 0.5, an R squared value of 0.10. And there's less predictive power in each. So it's the relative strength index for regression. So that's what I was saying. It's the strength of that relationship. Sometimes we refer to it as the coefficient of determination. And mathematically, it works out to the ratio of explained variation to the total variation. Here, I'm going to show you how to do that in Excel real quick. So I've got my data analysis and regression right here, right? Got regression, and I choose the predictor. The Y value is first. See, Y range. The Y range is what I'm trying to predict. That's the average date of spring thaw. Okay. And then I choose the X range. That's the latitude. You see, that's the reason. The reason why that's the X is because we're using latitude to predict the Y value. And then I'm going to put this in, I'm just going to put it in a new worksheet ply. I'm also going to check, for now I'm going to check these and we'll come back to what they are in a second. Okay. Say okay. It's going to put it, here's our new worksheet ply. And this is what the book shows up. All right. So here is our R squared value right there. There's the R value, which is the correlation coefficient, and there's the R value itself. Okay, let's talk about a few more of these things, and we'll come back and reference this. So one of the things I just did right there. So another way to think about the variance is the sum of the squared differences, just like standard deviation is. Standard deviation is a measure of variance, right? It's actually the square root of the variance, technically. So all this value right here is the total sum of squares of all of the predicted values in the regression, all the little predicted values. This is the total variation. In fact, an easier way to think about this is that these residuals are actually the sum of the squared differences between the model. I'll go back here real quick. Where's that other chart? This one right here. See all these distances right here? The sum of all those squared distances from the model down to the or up to the actual value. Those squared differences, those are right there. And another way to think about that number is that it's the unexplained variance. It's the stuff that's not explained. It's the difference between the value and the model. So we add all those up, we get the unexplained variance. And this number is just the total variance minus the unexplained variance gives us the explained variance. I can show you. Equals this minus this. See how that number and this number are the same? Okay? And so this R square value it works out to be this number squared, but it's also this number right here divided by this number. The explained variance divided by the total variance. And that's why it's going to always be a number between 0 and 1. Because as you explain more and more variance, you're getting closer and closer to 1. All right. Which slide was I on here? Okay. If we multiply R by 100, we get the percentage of explained variance. Also, we could think about that as the percentage of water removed by the sponge. Okay. R and R squared, they're closely related, but they have different interpretations and purposes. Okay. So, R is the level of association, and it doesn't imply a functional or causal relationship. It's just how one value is related to the other. R squared requires a logical rationale, and it's specified at the specification of explanatory and response variables, and it measures the strength of the power of the model that was created. All right. So the unexplained variation is the difference between the actual values and the predicted values. So it actually created all those residuals for us. So this table right here, when I check that, this is the predicted Y value, and this is the difference between the predicted Y value and the observation. So another way, let's see if I can just, I wonder if I can just take this part of it. Control C and put it back into the other table. I'm gonna have to move this over though. Okay. Let's make sure that the observation numbers are the same. Yep, they are. So that's why I don't need this anymore. All right. So this is the actual date of last spring frost. This is the predicted value, and this is the residual, the change between those values. Okay. So 19, 17, 10, let's see if those numbers actually work. This minus this. Yep, that number, see how that number is the same? So these are the differences between all of them. So one of the things that we can do with that is we can look and see where the biggest residuals are. So we could go back in and make a map of this data and see where the biggest residuals occurred. That would actually probably be fairly useful. Let me just take all of this data. No. I don't want to get any actually, before we map the data, which I think will be useful, I want to get to talking about what this last thing means. So this last column that says standard residuals. Okay. The absolute residuals are important. We'll talk about the standard residuals in a second. The absolute residuals, they measure the amount of error associated with the data. We're going to map them in a second. It's kind of neat to see where they exist, and if there's a pattern to the residuals, it often indicates that there's some other variable that can be used to predict. Obviously, underprediction and overprediction are negative and positive in terms of the residuals. All right, let's talk about for a second standardizing the residual, because the raw residual itself is in the same units, which are days. So we're over-predicting or unpredicting by a number of days. So this column is in the same units as this column all the time. But what if we want to determine how different it is in terms of how unusual that particular value is in general terms? Well, in that case, we need to get a standardized residual. A standardized residual is actually, the measurement of a standardized residual is it's kind of similar to z-scores. So it's similar to the standard deviation. So that's this column right here. This column right here. And I accidentally overwrote some of those other values, but that's okay. So this column right here is the standard residuals column. And we can map that one too. So the standard residuals is the way you calculate the standard residual is you get the residual value and you divide it by the standard error. Standard error is really easy to calculate. So here, just the standard error is the difference, the sum of all the differences between the real values and the predicted values squared divided by n minus 2. So basically, the way that you would calculate that, if you wanted to calculate your own standard residuals, is you would take all the residual values and square them and add them all up, and then divide that number by 2. So you're kind of coming up with an average residual value, and then you're using that average residual value to standardize all of the residuals. So here's the residual square equals this times this. So those are all the residual values squared. And then this was going to equal the sum of all those values and you actually want the square root of the sum. So we'll go SQRT divided by n minus 2, which is 76, 74, I think, n minus 74. Yep. So then you take this value here, we're going to call this standard error of the residuals, and you say that's going to equal this divided by the standard error of the residuals. Must have calculated my values. Oh, no, sorry. Not this one. It's the actual residual, not the squared residual. There we go. And there must be an observation number missing here, because my number isn't quite the same as that number. Let's see if I just played with that number for a second. So instead of minus 2, I'm just off by a number, so we'll go to 75 maybe and see what happens to that number. Yeah. So n minus 2 must be 75, because that's the number that's going right there. If I filled this column down, those would all fill down. So that's how that number is calculated. And that number is useful when you're comparing two different distributions that are measured in different units, because it's the standard error. It's the standardized residual measured in standard deviations. How unusual is it? And then I'm gonna show this in ArcGIS real quick. But one thing to look at is to plot all of your residuals. This actually looks pretty good. There's a little bit of a pattern maybe out here, but not over here. And so if your residuals go like this, or have some sort of pattern associated with them, there's some other variable in your data, or your relationship isn't linear. Your relationship might be curvilinear. Okay, so let's do this real quick. All right, so I'm going to take the original data set. Yeah, I got it all. I'm going to copy this and put it in a new data set and just file, save as. CSV. Hopefully this works. I'll just call this arc. Yep. Okay, so I got ArcGIS open. I'm going to add in this CSV file. I don't even know where I saved it. Probably in downloads. And I called it DL. Well, I guess I didn't save it there. File, save as. CTemp. One more thing I got to do is ArcGIS does not like calling things CSVs. So I just got to change the extension to text. It looks like I have to close it out of here. Okay. Try again. There we go. So now I'm going to bring this into ArcGIS. It's in CTemp. Temp. It's in last spring frost. And it's this one. Okay. So hopefully this imported. Sometimes ArcGIS is finicky. But it looks like it imported just fine. So I've got latitude, longitude, and the average date of spring frost. I've also got all my residuals right there that I can map. So I could go ahead and make this into a map by saying add XY data and choose X field would be the longitude, latitude would be Y, that's right. And I'll put this in, say, okay. So there's all these points. It's southeastern United States, that makes sense. So now I can just symbolize however I want based on the standard residuals. So ArcGIS recognized that it was plus minus. And I've got a map of my residuals. It's kind of hard to see on that map. I'm going to make the dots bigger. Properties for all symbols. Something really weird's going on. Anyway. I don't know what's happening in my ArcGIS. Okay, go back to that. All right, they're bigger now. So we can see that we've got residuals, and there doesn't appear to be a huge pattern, okay? But in general, all of the negative values, which means that they were underpredicted, are mostly along the coast. You see that? I mean, it's not like a definite thing, but they're mostly along the coast. And the values that were overpredicted are mostly in the mountains. There's some exceptions. but they're mostly in the mountains or in the coast, the Piedmont area down here. There's some exceptions, but you know, you go like you draw a line right through here, and you only got a few blues on this side, and only got a few reds on this side. Okay, so that is an indication that you've got some other pattern in the data, and we know that there's another pattern because we looked at the correlation coefficients beforehand. Incidentally, before I go back to the lecture, you can do ordinary least squares regression right from ArcGIS. So I'm going to take this data set and save it as a shape file here real quick. Yeah, I'll put it somewhere else. See, temp, last, spring frost, I'll just call this okay, so I'm going to say okay to this, save it. So let's say we hadn't already run the data in Excel. There is a tool in ArcGIS for there's a toolbox, there it is, for doing this. Arc toolbox. There's a tool in spatial statistics under modeling spatial relationships. The book doesn't talk about geographically weighted regression, but I'm going to talk about it a little bit next week, and I'll talk about that in a second. Right now we're doing ordinary least squares. So ordinary least squares regression, we have the ability to choose a feature class. In our case, we're going to choose this last spring frost. And then we can select the, you have to have a unique ID field, otherwise it won't work. It looks like I have a problem. I wonder why. An integer field containing different values for every class in the input feature. To me, this one, I don't know why that's not, no, it's double. Okay, so this can be solved pretty easily. I don't know why that's a double. We'll go add a field. We'll call this UID, and we'll make it an integer. Short integer is fine. And we'll just calculate this SID value into there. Actually, we'll just calculate FID into there. So that's the auto-generated unique ID field. And for some reason, it can't be that field. So now when we select last spring frost, it should let us choose this one we've created. Yep, and it does. So the dependent variable is the one that's getting predicted. In our case, what is that? Yes. And then the response variable, we're just going to choose latitude. Now, this allows you to do multiple regression, which is the topic for next week. So you can select latitude and distance to coast together. And then the R-squared value tells you how much explained variance there is with those two variables instead of just one variable. But for now, we'll just run it with the latitude variable. And we're going to output our report file to the same location, C temp last spring frost, and we'll just call it report. That's probably a bad name. We've got some additional options here. You could output the correlation coefficient table. That's the correlation between each of the individual variables. Since we only have one variable, it'll appear in the report, so that's fine. And then the diagnostic table, which will give you all the significance test results, which will also be in the report. So we'll leave that blank for now. And I'll say, okay. Now this is going to run. Close this now that it's going to run. And what we can do is look at the report. Did it run? Show processing results. It did run. I wonder where I said I was going to put it. I thought I said I was going to put it right there. Let's try rerunning it. Let me see where I was. So that's where it put the data. Let me actually put it somewhere else so that I can get to it. Explanatory variable, latitude, that should work. Okay, I think I need to reboot my my system because I was having this problem yesterday. See, it didn't even produce the output. So I'll have to do that between class. But you can do ordinary least squares regression right inside of ArcGIS. It is possible. Actually, why